Nathan Bowler from Hamburg.
Yeah, good afternoon. So I am very grateful to have a chance to talk to you today, and for the following reason. I have a question that I want to ask you all, and it's a question where I think probably if somebody in the world can help with this question, then also somebody in this room can help. And so, the question has the following form. It says, here are a bunch of games, and here's another bunch of games. If these are all determined, do these also all have to be determined? Okay, and we'll see concretely what the games which come up are a little later on. They're not too complicated. And it seems like there ought to be some methods for attacking problems like this, but I've not come across anything anywhere. And I think maybe having a particular concrete problem like this helps to focus on what sort of ideas are needed to this sort of a question. Right. Now, the question came up in the study of infinite matroids, which is what Johannes was just talking about. And so I'm going to tell you a little bit about how this question arises. And if I sort of start getting into sort of, or using weird technical words about infinite matroids, which I might do because I'm very used to them, then please just stop me, or if anything's confusing, just ask some questions. I should also say, if you've only seen infinite matroids for the first time this week and you don't feel completely comfortable with them, don't worry. The exact details of the definition are not important for the question. So you should be able to understand the question and even to think about it, even if at no point during my talk you ever come to understand what an infinite matroid is, somehow in your gut. Okay. Right. And I want to start by talking about a way to build some examples of infinite matroids, a way which gives you a lot of freedom. And I guess first I want to talk about a simpler construction which lets you build slightly bigger finite matroids out of smaller finite matroids. And the idea is to stick two matroids together in a way which looks very much like a standard way to stick finite graphs together. And throughout the whole talk, if you just don't want to think about finite matroids, whenever I say finite matroid, you can just think finite graph, and you shouldn't lose very much. So if we have two finite graphs, like this, say, and we nominate an edge in each of them, then we can try to stick those two graphs together along those edges by identifying one end vertex here with an end vertex here, and the other end vertex here with the other end vertex here, and then throwing away the edges. So here, when we stick these two graphs together, we would end up with this graph here, where we've somehow thrown away this gluing edge. This doesn't appear in the final graph. Okay, so Johannes defined matroids in terms of circuits, and so to understand how we could have a corresponding operation on matroids, we should look at what happens to the cycles in these graphs, what the cycles of this newly built graph look like. So let's say we've now stuck together two graphs over here along some edge. What do we get as our cycles in the new graph? Well, we have some cycles which just lived in the left-hand graph and didn't use this edge. We have some which lived in the right-hand graph and didn't use this edge in the middle. And we have some which now are going across between the two, but they can be built from a cycle of the left-hand graph, which did use this gluing edge, and a cycle of the right-hand graph, which used the gluing edge. So what we'll do to stick two matroids together is we'll just take our new cycles to be precisely the sets which arise in this way. So old cycles of either matroids that don't use the gluing edge, or things obtained by sticking together cycles of the respective matroids which did use the gluing edge. Okay. And I should point out, this works nicely with respect to the duality of matroids. If you dualize both the matroids, then when you stick them together, you get the dual of the thing you got by just sticking the matroids together. And we can kind of see that phenomenon already in finite graphs, because the circuits of the dual matroids, and in general I'll call a circuit of the dual of a matroid a co-circuit of that matroid. Okay, so the co-circuits of the matroid we get by sticking together these two graphs should be just the bonds. And what can a bond do? It has to decide whether to put these two vertices on the same side or different sides. If it puts them on the same side, then it's just a bond like this on the left, or one like this on the right. But if it puts them on opposite sides, then it's just built from a bond of the left-hand graph and a bond of the right-hand graph, each of which used the gluing edge. So it's just the same as before. Okay, so something else I want to say about this operation is that it is associative. So, yes?
Something I've seen in a similar context, I'm not sure it's correct here
Yeah.
also, that when you glue the graphs, it makes a difference which way you identify the edges, but on the matroid, it makes no difference, right?
That's absolutely right.
Okay.
Yes, thank you. Right. So we could think of this graph here as having been obtained by sticking together maybe two copies of this complete graph on 4 vertices. Right. And now it doesn't matter whether we stick, first of all, these two together and then stick this one on, or whether we do it the other way around, stick these two together and then stick this one on. This operation is completely associative. And normally associativity means it doesn't matter somehow how you bracket a string of things. But here we're sticking together graphs, so we have a bit more freedom, and it says it doesn't matter how you bracket somehow sticking together a tree of things. So generally the situation will be you have a bunch of graphs arranged in a tree so that maybe adjacent graphs have an edge that we identify, and now we can glue them together along those edges in this tree, and it's completely unambiguous what order we do that in. So what do the cycles now look like when we glue things together like this? Well, they could live locally within just one chunk, or maybe they should cross some of these separations. So each such cycle picks out, in some sense, a collection of nodes of the tree which that cycle uses. And that collection is a subtree of the tree that we started with. So to get a cycle, we'll take a subtree of our tree, and at each node of that subtree, we take a circuit of the corresponding matroid, a cycle of the corresponding graph, which contains precisely those gluing edges which correspond to directions in which the tree continues. Okay? And that is how this operation is defined in general. Okay. So now we could have the following idea. We could say, if we want to build an infinite matroid, we could try to stick together a bunch of finite matroids, maybe infinitely many finite matroids, but along an infinite tree, right? Just following this construction. And if we try to do this, we run into the following problem. So let's try to stick together, let's try to sort of extend this construction infinitely far to the right. Let's try to stick together infinitely many copies of the complete graph on 4 vertices. Okay, so now this is some graph, and so we could look at the two different matroids that Johannes talked about for this graph, namely the finite cycle matroid, whose cycles are just finite, whose circuits are finite cycles in here, or the topological cycle matroid, where you're also allowed double rays that head off towards this end. And both of those seem like good candidates for the matroid obtained by sticking together all of these different finite matroids. What's the choice that we're making there? Somehow the choice is whether the subtree on which the circuit is defined is allowed to extend infinitely far towards this end or not. Right? If you only allow subtrees which have to stop at some finite point, then you'll get the finite cycle matroid. If you allow them to go all the way to the right, then you'll get the topological cycle matroid. Okay. And we don't want to simply say, okay, I decide for one of these options. Maybe I decide to always do the finite thing where you can't extend infinitely far, because then we lose this nice duality property, right? If I take the finite cycle matroid and I dualize, then I get some infinite bonds, and they do want to go all the way over. All the way over to the left. And if I allow the infinite cycles and I take the dual, then the co-circuits are now not allowed to go infinitely far to the right. So instead, what we're going to do is we're going to somehow welcome this as an additional freedom in this construction. We're going to say that not only is our data for building an infinite matroid an infinite tree of finite matroids, but also we allow ourselves to make a decision at each end of the tree about whether or not, about whether that end prefers to be used by circuits of the matroid or by co-circuits of the matroid. So let's say we have now some infinite tree, and we're going to take, as part of the data of our construction, some set of ends of the tree, which I'll call psi. An end of the tree is, I guess formally you could identify them with rays through the tree from some arbitrarily chosen route. Okay. Yes. And how are we going to define the circuits? Well, we're going to do just the same thing we did before. We're going to take things that come from picking circuits locally along some subtree of our tree, but where we now require that every end of this subtree, every way to go through to infinity through this subtree, should actually prefer to have circuits there, so it should be in the set psi. Okay? And to get the co-circuits, we'll do just the same, except that we'll take the complement of the set psi, right? We'll say all the ends of your subtree have to go into the complement of psi. Right. Okay. And now I suppose I should reveal, so there's not too much tension, this doesn't always give a matroid. But what I want to do is try to explain to you under what circumstances this gives a matroid. And what we need to do is we need to check something like this axiom C3. And there's a trick which in many contexts makes it easier to check this axiom C3, which is to check some axioms which are slightly easier to work with, but which are expressed not just in terms of the collection C of circuits, but also in terms of the collection D of co-circuits. So let me write those axioms down. These, incidentally, are the axioms that Johannes mentioned in his open problem. They're the Minty axioms, where we want to know if they guarantee that you have a matroid on an uncountable set. Okay, so these are O1, which is simply the property that that you never have a circuit which meets a co-circuit in a single edge. Right. And the second axiom is a little more complicated. It says if we take the edge set of our matroid and we partition it into two parts P and Q with a single edge E left over, then either it's possible to span this edge from P, that means there should be some circuit which uses the edge E, contains the edge E, and otherwise only contains edges from the set P, or else there should be some co-circuit which contains the edge E and otherwise only uses edges from the set Q. Let me write that precisely. So for any partition like this, either we get that there is some circuit which spans the edge E from P, or else there is a co-circuit which spans it from Q. Okay, so maybe to understand what's going on here a little, we should see what this means if we interpret it in a graph. So now curly C will be the set of edge sets of cycles, curly D will be the set of bonds. So here's our graph. Let's say here we have some edge E, and we've also got some edges of the graph that we've put into a set P. Okay, so this is going to be P, and the rest of the edges are in Q. And now, in order to get a cycle containing this edge and otherwise only using edges of P, what we need is just a path through P, a path through P joining the two end vertices of the edge, right? And if we can't do that, it must be that actually these two endpoints can be separated in a way that doesn't meet P, right? I mean, we could just take the component of P containing this vertex against everything else, right? And that would give us some cut of the graph that doesn't meet P but contains the edge E. So that's roughly where this axiom is coming from. Okay, and I said that from these two axioms, we can now get C3. We can get this axiom over here. Why is that? So what we want is a circuit which contains this edge Z and otherwise only uses these white edges that we haven't yet eliminated, right? And that looks like maybe the first option of the two things in O2. So in order to show that that happens, we have to show the second one can't happen, right? We have to show that there can't be a co-circuit which contains this edge over here and which otherwise avoids all these white edges that we haven't yet eliminated. Okay, so where could this co-circuit go? It certainly met this circuit here at least once. So by O1, it has to meet it again somewhere. It has to somehow escape somewhere, and it could only do that in one of the edges we eliminated, one of the edges of X. Okay, but now it has to meet the circuit that we stuck on at that edge again, somewhere else, again using this axiom O1, and so it really does meet this white set again somewhere. So, so that shows that if we have those two axioms, then we get C3, and actually it turns out, in general, having these axioms in this context of these trees is equivalent to having a matroid. Okay, good. So now let's try to understand the meaning of these axioms when we apply them for some such tree. Okay. for which tree? Well, let's do it for the tree where at the bottom we take a copy of this graph, which branches somehow both to the left and to the right. And on each of these gluing edges, we just stick a hexagon. And we carry on building a binary tree, alternating copies of this graph and hexagons. So maybe here we should have another copy of that graph, and also here. Right. And also over here, and maybe some hexagons on here. Right, and so on. Okay. And now I ought to tell you which edges go into the set P and which edges go into the set Q, and essentially all edges will go into the set P except these sort of central edges of these graphs which appear at alternate layers, and of course also apart from the edge E, which will be here at the bottom. Okay, so now, what does this top clause of O2 mean in this context? I should say, I'm not going to check O1 in this context. O1 is very easy for all such trees of matroids. But O2 is much more interesting. And this top clause says we should have some circuit which contains this edge E and otherwise only uses yellow edges. And that should be built out of some subtree with local circuits at the nodes. And the subtree certainly ought to contain this node, because we want to use the edge E. Right? And what could it do at this node? There are really two options. It could have this cycle going up here to the left, or it could have this one, let's take this one, going up here to the right. Yeah, I mean, we're not allowed to use this little cycle in here because this edge isn't in the set P. So we get to choose, and once we've chosen, we know that our subtree has to extend in this direction. Okay, and in this direction, our only option is to take the whole hexagon here. And that means now we have to extend in both directions. Okay, but having extended, say, in this direction, we again get to choose which way to go, and then again we have to go in both directions here. Again, we get to choose where we're going. So in order to get such a cycle, we have to find some subtree of our tree which at alternate layers either branches in both directions or branches in at least one direction. You get to choose a direction. And it should have the property, which I mentioned earlier on, that all the ends of this subtree, all the ways of going to infinity, should be in our set psi of ends that are allowed for circuits. Right. But if we consider what that means, that just says that to find a circuit, you need to find a winning strategy for the first player in the game where the two players alternate, picking elements of the set 0, 1, and where at the end the first player wins if the sequence they generated between them is in some set psi. Right? And if you look at this second clause, what it would mean to find a co-circuit, then just by a very similar argument, you can see that that's the same as having a winning strategy for the second player in that same game. Okay? So that means that this axiom O2 in this context simply becomes determinacy of a particular game. Right. Now this was a very special example of a tree of graphs constructed to make that very obvious, but actually this is true completely generally. So what do I mean by that? I mean, for any instance of O2 in some tree of Matroids, there is a game which you can easily construct from that instance of O2, such that that instance of O2 is satisfied precisely when the game is determined. Okay? And what is the game? It's the obvious thing you would think of to try to witness this first condition from O2, right? It's a game in which one player tries to build a circuit witnessing this first condition, and the second player tries to get in their way. So, more precisely, let's say we have our edge E down here at the bottom. The first player says, all right, in this node on my tree, I want to use this circuit here, right? And let me do one which uses both of these glowing edges. Right, and then the second player is a bit skeptical and says you certainly can't carry that on. I mean, maybe you could carry on in this direction and you'd be fine. But in this direction, you're not going to complete that to a circuit. So the second player just challenges on some gluing edge which appears on that circuit. And the first player says, well, all right, if I carry on in that direction, maybe I want to use this local circuit. And again, the second player has to challenge on some gluing edge, and they carry on happily through the tree in this way. And and if they manage to keep going for infinite time, then we say that the first player who's trying to build a circuit should win precisely when the end of the tree that they've gone to is in the set psi. Right? This is the obvious game you would consider. And this game, as I say, is determined precisely when the corresponding instance of O2 is satisfied. So, yes? So yes, the first player wins precisely when the first clause of O2 is satisfied. And it's not so obvious, but it's true. The second player wins precisely when the second clause of O2 is satisfied.
So if all these games are determined, you've got O2 then?
Precisely. Yes. Precisely. This construction of a tree of Matroids giving you a Matroid is equivalent to a bunch of different games all being determined. Okay? That's what happens here. And now all those games are easy to build from the set psi. So if it happens that the set psi is in some class of determined sets, which is closed under inverse images by continuous functions, then we'll certainly get that all those games are determined, and this will be a Matroid. So for example, if psi is Borel, or if we have analytic determinacy and psi is analytic, or if we just assume the axiom of determinacy. Okay, any of those would give us a Matroid here, but it could happen that we get a Matroid here, but not for that reason, somehow accidentally, that all of these different games end up being determined, but not because they're in some nice class of determined sets. Right? It could happen. Keep that thought in mind. And also, remember this game. This game will be important later on. Okay. Good. So, yes, now I want to tell you about a conjecture about infinite Matroids. It's about a very special class of infinite Matroids called directed infinite Matroids, and they should be thought of as being like directed graphs. So remember that a directed graph is just like an ordinary graph, except that we also choose a direction for each edge of the graph. Maybe this one this way, this one this way. Okay. Something like this. Right. And now, something we can notice about cycles in directed graphs is that if I have a cycle, then maybe some of the edges.
No, you mean directed cycle.
I mean a cycle together with a chosen orientation of that cycle.
That's what I mean.
Yeah.
Directed cycle.
Okay, great. Some people use directed cycle to mean oriented cycle, and yeah.
Oh, all right.
Okay. So, right, if we have such a cycle, then some of the edges on that cycle are going somehow the right way around it, and some of them are going the wrong way around it. So we can sort of pick a function, we can find a function on the set of edges of that cycle which tells us some of them are going the right way, let's give them a +1, and some of them are going the wrong way, let's give them a -1. Okay. And this is true not just for the cycles of the graph, this is also true for the bonds of the graph. Let's take some typical bond. We've got some edges going across the bond, and these should now be directed. So maybe some of them are going this way, and some going this way. Right? And so again, we can find such a function where we'll say maybe +1 if it's going across the bond one way, and -1 if it's going the other way. Okay. So let's make this precise. A directed matroid is a matroid together with such functions, which I'll call signings. Together with so if I have a circuit C, I want a function from C to the set ± 1, and I'll call that C arrow. Right. And assigning, so similarly assigning D arrows for each co-circuit D. Right, and obviously we have to have some restriction on these functions. They're not just going to be chosen arbitrarily. And what is that restriction? Well, if I take a cycle in the graph, which maybe goes back and forth across this bond, then I can always tell which way across the bond the cycle is going, right? Maybe when it's going in this direction, the two signs of the edge agree, and when it's coming back, they disagree, right? And what I want is that just as in any graph, the cycle crosses the bond the same number of times in each direction, right? So formally, that means that when we take any circuit and any co-circuit, we want there to be the same number of points in the intersection where the signs agree as where the signs disagree. And formally, we can simply express that like this, that the sum over all elements of the intersection of the product of the two sign functions should equal 0. Okay, so that's a directed matroid. Right. And examples are given by directed graphs. Right. So now, I don't need C3 anymore. So now, let me state the conjecture about these things. And in order to do that, I need to define oriented circuits, not to be confused with directed circuits. So an oriented circuit is one for which the function C arrows is constant. Right? That means all the arrows on the cycle are just pointing the same way around it. Okay, and the same for co-circuits. Right. So now the conjecture is in a directed matroid, the conjecture is that each edge should either lie on an oriented circuit or else an oriented co-circuit. And this has been open for many years, but I don't know, it seems like it ought to be true. Let's check why this is true, or what this means in the case of directed graphs. Here's some directed graph. Here's our edge E. And now maybe we'd like to find an oriented circuit through E. That means we should try to find some directed path through the rest of the graph, going from this end of E around to this end of E. And if we can't do that, again by some kind of max flow min cut type principle, it must be that the reason we can't do it is that there's some cut of the graph which witnesses that we can't, in the sense that all the edges of that cut are pointing the wrong way. Right, and that's exactly giving us an oriented co-circuit through the edge E. Right, so this is somehow a vast generalization of this principle. Okay. Good. So what will happen if we look to see what this conjecture means in the matroids that we were considering earlier, the ones built by sticking together trees of finite matroids or finite graphs, let's say? Well, first of all, if all the matroids that we stick together are already directed matroids, say if they were all directed graphs, then it's not too hard to put a directing structure, so to find these signings on all the circuits of the matroid we get by sticking this together. So the point is, if we have maybe some, right, I'll do it here. If we have some circuit and we want to know whether two edges are pointing the same way or different ways on that circuit, if they live in the same blob, then it's easy to compare them. We just use the comparison from the directed matroid at that node. If they're in adjacent nodes, then we can compare this one with the gluing edge and then go on to compare the gluing edge with this one over here, right? And so that allows us to compare and see whether an edge over here and an edge over here should have the same sign or should have different signs. And then we can just carry on through the tree in the same way. So maybe we have an edge down here and an edge up here. Right, maybe this has the same sign as this gluing edge, then this gluing edge has a different sign to this gluing edge, and then this one has a different sign to this gluing edge. Then we had different signs twice, so we should give those two the same sign. Something like this. So that gives us a directed matroid, and this, if you define it that way, it's not hard to check that this condition will hold for those signings. Right. So the question becomes, when would this conjecture hold? in such a signed matroid? In such a directed matroid? And the answer is, once more, that for this to hold at an edge E is equivalent to the determinacy of a particular game. Okay? And once more, it's precisely the game that you would expect. It's the game in which one of the players is trying to build this oriented circuit, and the other player is trying to get in their way. So the first player looks on this node and says, right, I'll pick, maybe E is oriented this way, I'll pick some local oriented circuit. Of course, that just means the orientations on the non-gluing edges have to be going the correct way, right? We don't care about the orientation on the gluing edges because we're going to throw them away later. And then the other player says, right, I don't think you can carry on this way, and makes a challenge. And so the first player, the one who's building the oriented circuit, then carries on by giving some local oriented circuit in this node. And again, the second player challenges, and they carry on to infinity. And once more, the first player wins precisely when the end that they go to is in the set psi. Right? So the only difference is that now, in this game, the restrictions on the circuits are that the orientations have to be correct. Whereas previously the restriction was that you could only use edges from the set P. Right? Okay. And so once more, it's true, if the first player has a winning strategy, you get an oriented circuit. If the second player has a winning strategy, you get an oriented co-circuit. And so determinacy of this game is equivalent to the truth of a particular case of this conjecture. Okay, and so the truth of this conjecture for the case of a particular tree of finite matroids is equivalent to determinacy of a whole bunch of different games. Right. And if we built this matroid sensibly by maybe taking a Borel set of ends to guarantee that it's a matroid, then we also guaranteed at the same time that all these games are determined. Because again, they're all somehow inverse images of this guy by continuous maps. But if this guy was a matroid just at random, right? If the first things were just all happened to be determined, then it's not clear whether these other games will end up being determined, right? They're just a different bunch of games. And so, yeah, that's what I would like you guys to help me understand. When is it the case, or like, how would we show that if all of these are determined, then all of those are determined? Or can we maybe build some example where all of the first bunch are determined, but one of the last lot isn't? Right? That would then resolve this conjecture. Okay. Good. Okay. Now I should admit that although this conjecture has been open for a long time, and I find it very frustrating, I don't think this is the most important conjecture in infinite matroid theory. This isn't, I think, an especially deep conjecture. Okay, so why have I gone to the trouble of telling you all about this conjecture for an hour? The reason is that there's another, much deeper conjecture, I think the most important conjecture in the theory of infinite matroids at the moment, and one with deep implications for a lot of infinite graph theory, where the same phenomenon, exactly the same phenomenon, shows up, right? Where if you look at what it means for these guys built by sticking together trees of finite matroids, then you find that the truth of the conjecture is equivalent to determinacy of a whole bunch of games, just built in a simple way from that tree, right? And so I think an answer to this, maybe toy version of that question, would be very likely to then lead to an answer to this question that I'm much more interested in. So let me, I have a few minutes. I'll tell you something about this slightly deeper question. So this is called the matroid intersection conjecture, or the packing covering conjecture, and it was mentioned by Jurek in his talk on push-down automata and infinite matroids. He said what this conjecture is. Let me rephrase it a little, because I'm talking in terms of circuits in this talk. So what does it say? It says you have two different matroids on the same set. Then you can find a subset of that set and a partition of the set with the property, first of all, that there isn't any circuit of either of the two matroids included in this set. Sorry, there isn't any such circuit. And secondly, somehow...
You mean there is neither or...
Right, there is neither a circuit of the first
okay.
matroid included in the set, nor a circuit of the second matroid included in the set. But for each edge out here, we can't add it to the set, and for a very special reason. So for the ones over here, we can't add them because there's a circuit of the first matroid which spans them from just the left-hand side of the set. And for the edges on the right, the reason is that there's a circuit of the second matroid which spans them, again, from just the right-hand half of the set. Okay. So that is the infinite matroid intersection conjecture. It's not very illuminating when you first see it. It's not clear what this is really talking about or what this means. So let me tell you about something that you can do with this. So I guess I want to tell you about...
Could you just repeat the quantifiers again? I guess.
Yes.
So what is the question exactly?
Right, so the question is, you have two matroids on the same ground set. Must it be that there is a subset of that set, together with a partition of the set into
And
two
the
halves,
partition, yeah.
with the following properties? The subset doesn't include a circuit of either matroid. And for each edge in the left half of the partition, but not in the subset, it's spanned from the subset by a circuit of the first matroid, and for each edge over here in the right-hand side of the partition, that should be spanned from the right-hand side of the subset with a circuit of the second matroid.
Thank you.
Okay, good. Right. Okay, so I guess I need to make a slight digression and tell you about a very useful result from the theory of finite graphs. So the question is this: we have a finite graph, and we have two sets A and B of vertices of the graph, and we want to know how many disjoint paths we can find going across from A to B. Okay, so if we can find a set of vertices such that when we remove them, that separates A from B, I'll call such a set an AB separator, then the size of that set certainly gives us an upper bound for the size of such sets of disjoint paths, because each path has to go through one of the vertices. Okay? And Menger's theorem, again a kind of a max flow min cut thing, says that actually that's the only restriction. So you can always find some AB separator which consists, which is the same size as the largest set of disjoint paths from A to B. Okay, now Erdős was thinking about what you might do if you wanted to generalize this to infinite graphs, and he came up with the following idea. He said, maybe we just take the same statement, but every time you said size, you instead say cardinality, right? So there should be some AB separator of the same cardinality as some maximal collection of disjoint paths from A to B. And it's true, you can always find such a separator of the correct cardinality, but somehow, I mean, Erdős didn't just prove this statement, he proved that this statement is basically the same as the finite version. I mean, there's no more content to it. And so he also came up with a conjecture of a generalization of this, which is much, much deeper, which somehow encodes some structural information about the graph. Right, so the idea is to look at what structural information is encoded in this equality between the size of a smallest separator and a largest set of vertex disjoint paths, and the answer is that this guarantees that in any graph, if we have such a pair of sets of vertices, we always find a set of disjoint paths from A to B together with a separator consisting of precisely one point from each path. Right? So Erdős conjectured, right, this should be true for infinite graphs. Right? This was the Erdős-Menger conjecture. And this was open for decades, and people proved various special cases of this, maybe rayless graphs or countable graphs or all kinds of things. Finally, this was proved in 2009 by Aharoni and Berger, and their proof is one of the deepest proofs in combinatorics right now. This is a really deep proof. And yet, this statement follows without too much trouble from the Matroid intersection conjecture, right? So it would be really neat to find a kind of a more abstract proof of this. I mean, not only because we could recover this statement, but because we could because we could get all kinds of similar statements to this, but it may be in topological context or any context where we can find matroids instead of just graphs. So yes, there are a bunch of other ways that you can use this to get statements in infinite graph theory, but I don't have time to go over them, so I think I'll stop there. Thank you.
Yeah, thank you very much. So, any questions?
Well, you said that this connection is not without not with too much trouble.
Yes.
Can you tell us a little bit?
Yeah, sure. What you do is you take. Okay. You want to find two matroids on the same ground set. Right? Here's how you build them. You take the finite cycle matroid of the graph, okay, and you build two different matroids from it. In the first one, you contract. I suppose I should say, first you do a little bit of preparatory work. First you put in some extra edges to join up this set, and some extra edges to join up this set. Okay. Yeah. Then for the two matroids, for the first one you contract these edges, and you remove these edges. And for the second matroid, you contract these edges and remove these edges. So that gives you two matroids on the set of edges of your graph. And then if you have intersection for those two edge sets, somehow this set in the middle has to be independent in both of the matroids. So it kind of looks, maybe I'll make a new picture over here. Kind of looks like you have maybe some trees over here, and maybe some components which go and touch both of these sets, and maybe some components which hang on just one set, but you can't have a tree which somehow touches one of these sets twice, because then it would then it would include some circuit when you contract that set. Right? So that's not allowed. So you get some things hanging off like this, some things up here, and some which maybe touch both sets just once and look vaguely tree-like. And of course you get some partition. Right. And now what happens is that each of these trees contains a unique path from the left to the right. And this partition gives you a separator from A to B, namely the set of vertices which meet edges on both sides, which are incident with edges on both sides. And now that actually gives you such a configuration in the graph. I mean, there are details to check there, but that's how it goes.
Yeah, some more questions? All right, then let's thank Jason again.